Hello again, everyone. I hope you had a good lunch break. Gonna try to keep you awake now. So some of you, if you saw my talk this morning, I'm gonna talk about a similar topic, but about lab characterization of sensor and not field characterization of sensor. This is a bit about math. So actually, I'm not a mathematician. My colleague Guillaume is a math person in the group, so I'm gonna give physics side of things and not the math one. And it's a paper from IEEE Sensors Journal from Université Gustave Eiffel, and within the framework of the Lotus project, which aims at providing water quality sensor for India. Beyond just water quality, environmental pollution, air or water, this is 9 million deaths per year, as per 2022 estimate. And everyone knows that reducing pollution requires diagnosing the sources, diagnosing exposure of people, counter, optimal control of automation system, and performance assessment of the solution that you're deploying, such as traffic policy. So this is something everyone knows. And that's why people are developing sensors. That's why we're here. And we want to have massively distributed, low-cost environmental monitoring. The sensor market, as a consequence, is going up. But is it going that up? The answer is not that much. You see, it starts going up slightly in 2023. The reason it's not going up that fast is because some of these sensors are extremely complicated. You know, these are mostly the chemical sensors. And you know, if you're there, probably you know that chemical sensors for air and water still requires a lot of work, innovative concepts, innovative materials. The consequence is these sensors have a huge number of interferents. They still have lots of interferent parameters. The calibration laws are extremely complex. And on top of that, when you try to calibrate your instrument, the reference instrument that you're using, your reference are often not that accurate. Even if you pay a lot of money, you don't have perfect measurement. And the consequence is these sensors have chronic calibration issues. I'm going to give an example of that on my Lotus sensor again. The concept is a chemical resistor. So the resistance depends on the chemical environment because you put a sensing material here that reacts to the environment. And in this Lotus project, the sensing material, it's carbon nanotubes. So these are wires of carbon that are functionalized or not. With chemicals, and carbon nanotubes in themselves are not very selective, so the functionalization provides selectivity. So this is a typical outlook of the material itself, and this is the probe that we're using in this paper. It's called that we developed and patented in-house a couple of years back. In the end, you have a sensor array on silicon. This is 1 centimeter by 1 centimeter, and that contains here you have 10 devices with carbon nanotube non-functionalized, and here you have 10 carbon nanotube sensor functionalized. So you have a 2 by 10 sensor array. On top of that, you have also conductivity and temperature sensor, but that's not the point today. Just to have the rest of the story, this sensor can be integrated into a PCB, into a sensor head. Then you have an electronic card that reads all the sensors, sends it to the user, and it is integrated into a packaging that can be deployed in field conditions. So this was tested in water distribution loop. But today, what I'm going to talk to you about is the lab calibration only. So this is data from a typical calibration for this sensor. So you take one sensor and you do 3, 4, 5 days of calibration, and you get this kind of data. So this is 25 points. On top, you see the target parameters. These are chlorine and pH. Then at the bottom right, you have the output of the sensor. This is the example from one single sensor. And left, you have the temperature, which is considered the main interferent. The different colors are the different days of experiment. So the experiment went on for 4 days. So this is a big fail. it works extremely well in chlorine, but no way you predict pH. It doesn't work for pH. You have terrible performance in pH. To give you an idea, here the range of pH goes from 6 to 8, and you have error around 1 pH unit, so it's terrible. The reason why, the sensitivity to chlorine, we discovered, if you work in tap water, it's 5 times higher than the sensitivity to pH. And on the other end, it happens that the chlorine instruments, even in the lab, they are pretty bad. They have high uncertainty level. So if you multiply your high sensitivity with your high uncertainty, the variation is of the same range of magnitude as your sensitivity to pH. So you can't see pH because you don't know your chlorine well enough. So our work, this work was motivated by this discovery that we need to include uncertainty in the model. It's not really a discovery. We know uncertainty is important, but you don't always include that directly in the model, and that's what we did. So let me now put on the mat, sorry. dn is my calibration data set. So basically I have n observation in a calibration data set. An observation contains the target quantity, which is known with uncertainty. It contains the measured sensor data with uncertainty as well. And you measure interference also with uncertainty. And your job is to find the function f that is the calibration model. And it might not be explicit, it might not be analytical, but you're looking for that, guys. It's a core assumption that you can find the calibration. And you want your calibration data set to find it. However, we acknowledge the fact that we may not know the calibration very well. We may have error, like your model is exponential and you're just taking second order law. So this is, you assume you're going to be wrong. Another reason you might be wrong is because you don't, for instance, you know your sensor will depend on hardness, but you cannot measure hardness. So this is an interference you know, but you don't measure. And then there's also all you don't know as well. So based on that story, we decided to treat all the variables as random quantities and use Bayesian formalism. People who do probability, statistics, data science, they know this by heart. I didn't, I learned. So basically what we do is we say, we're not looking for the value of the target parameter, we're looking for its probability distribution. So you take the probability distribution of the target parameter, pH and chlorine, and you look for that, knowing a value of the output and knowing a value of the interference and knowing also your calibration data set. So this is your target. Pay attention, you know, probability distribution function. So this means that you're not going to have just a value. You're going to have a confidence interval around your value. So you know how good your prediction is going to be, which is very important. And we don't do that enough. Based on Bayes' theorem, this thing that you're looking for, basically, it's a product of the probability density of X. So basically the distribution of your variable in time of your variable, like its range, like it's going from 0 to 5 in chlorine, or it's a positive always. That's an example of a prior distribution. And the likelihood function, which is basically the distribution of the output, knowing X, the target, and the interference, which you can learn from the calibration dataset. So this information you have if your calibration is well done. Simulation, how this method works. Once you written the math there, you do a lot of math that I'm not going to describe. They are in the paper, so you can go see that here. I'm just going to explain to you what it means. So we took a case study with 2 parameters, like our physical problem. And we took a log law and a piecewise linear law because that's basically what we see on the data. It's not far from that. We have 2 interferent parameters and 1 unknown interferent in the model. So it writes down like this. The beta coefficient are the constant here. And this is a typical output I get. So this is an example. I have a nonlinear model and I'm trying to do a linear regression. So of course it doesn't work that well. So your true value is the black point and your prediction prediction is the maximum of the probability distribution. So it's in the middle. You see you have a significant error. But what you see also is that your prediction, your confidence in your prediction in the horizontal axis is terrible. Basically, you predict a point, but your uncertainty is the full range. So you're not predicting anything in that direction. The color is the percentage of points within the confidence interval. Now, what can we do better? First, you can do a generalized linear regression, which is basically polynomial model. And you see it's much better. You reduce a lot this confidence interval. And you can do even further. So this doesn't include the fact that in your calibration, this guy, the chlorine and pH are not well known. There are uncertainty. If you add uncertainty further, you reduce further this cloud. And if you go even further, and instead of an explicit model, you use a Gaussian process as a calibration model, you reduce this cloud much better. And it worked tremendously well on the use case we had. So basically, these are all these use cases. SLR is single linear regression, GLR is generalized linear regression, and GPR is a Gaussian process regression. And the only method that predicts pH is Gaussian process regression with a model error and with accounting for the input uncertainties. So this calculation is a leave one out approach, which means you predict each of the points in the dataset knowing the 24 over. So it's not a true calibration. Right now, it's the first step. It works. Our metric is MAE here, but we have tons of metrics in the paper. You can go check that out. So this works. So now we pick that good model and we try to do a much better calibration. We do 80-20 split of the data set, and we do 100 split, and we do statistics over this split. And you get this kind of data, chlorine to the left, pH to the right. The blue line is, the dotted line is our instrument, the uncertainty on our instrument. The blue line is the result in the leave one out approach. You see that with this split, on chlorine, you get the same performance in a normal calibration. With pH, you have a little degradation. You have 0.3 error in pH, still acceptable for your use case, not great, but acceptable. And you're a bit higher than the leave one out approach. But it works. Instead of a 1.7, you get a 0.3 error in pH, which starts being acceptable for the application. So this being said, let me wrap this up. I think I'm out of time, actually. 2 minutes. Real life for chemical sensor, it's interference, it's high uncertainty. And one thing I didn't mention before, it's small data. Having a lot of data in your calibration is almost impossible. So we developed a method that is compatible with small data sets. It's not a CNN. A CNN, you would have as good results probably, but you need 10 times more data. We don't have this. And it's successful in the use case. Thank you for your attention.